Welcome viewers. In this video we'll see the voltage regulation of alternator. There are several methods available. In this video we'll see the synchronous impedance method or called as EMF method. Subscribe the channel for more videos and notifications. Soft copy of this material available in the drive. The link is given in the description box. Now we'll go to the topic, voltage regulation of alternator by EMF method. First we'll see the what is mean by voltage regulation. It is defined as the change in the voltage of an alternator as the load on the alternator is varied from load to full load, normal load to full load, and is expressed as percentage of rated voltage. So it is nothing but normal load to rated load, full load. The variation in the voltage is called a regulation. That is E phase minus V phase divided by V phase into 100. E phase is the voltage induced in the alternator. V phase is the voltage available at the load terminal. So E phase minus V phase divided by V phase is nothing but regulation. While multiplying 100, it is a percentage of regulation. So we need to find this value. We'll see what are the methods available for determining the voltage regulation. The different methods to determine the voltage regulation are direct load test, synchronous impedance method, or EMF method. So we are going to discuss this EMF method in this video. Second method, ampere turn method or MMF method, zero power factor method or Portier triangular method, ZPF, ASA method or modified MMF method, two reaction theory. So these are all the various methods to find the regulation of the alternator. Separate video available for all the methods. The link is available in the description box. In this video we'll see the EMF method, synchronous impedance method. Now we'll go to this EMF method. So synchronous impedance method or EMF method. So the data required to find the regulation by synchronous impedance method is, so you see what are the data are required. We need two tests are needed, that is armature resistance RA, open circuit characteristics, short circuit characteristics. So from these three we can able to find the regulation by EMF method. Armature resistance RA we need to find, then we need to perform open circuit test followed by open circuit characteristics, similarly short circuit characteristics. So first we will see how to find the armature resistance RA. So to find the armature resistance RA, this is circuit diagram. This is three-phase alternator. R, Y, B, three phases are available. The circuit is connected across R phase. So only we are going to measure R phase, other phases are equal. So this R phase is connected with DC supply, 220 volt DC supply through the switches, single pole switch, single pole double thrown switch. It is connected in series with the ammeter in order to measure the current flow. Similarly voltmeter is connected across the armature. So this ammeter will measure the current IA. Similarly this voltmeter will measure the voltage VA. Now the switch is closed. The rated voltage is applied to the armature across R phase. Rated voltage is applied. At that time we have to measure what is the current drawn by the armature winding. So from the voltage and current value we are able to find the armature resistance. RA equal to V by I. So formula R equal to V by I. So the rated voltage is applied. For that we are measuring the current taken by the armature. From these two values we are able to find the resistance. Now we'll see the procedure. So apply the voltage across the phase R and neutral. Find the current drawn by the armature using the ammeter. So from these two values we can able to find R equal to V by I. That is RA DC for the across the R phase, V by I. So there is a relation between RA AC with RA DC, that is nothing but RA AC is 1.6 into times of RA DC. So now we are able to find the armature resistance R across R phase. Now we'll go to the next one to perform the open circuit test and short circuit test. So this is the circuit diagram to conduct the OCSC test, open circuit and short circuit test. So this is the three-phase alternator. Here only we are going to perform the OCSC test, R phase, Y phase and B phase. It is controlled by the TPST source, triple pole single thrown switch. So it is connected by the triple pole single thrown switch. So this is the alternator. We are going to perform the we are going to identify the voltage regulation. R, Y, B phase is there. We can measure the current and voltage using ammeter and voltmeter. Can be close the switch by using TPST switch. The field is available. This field is excited by the separate DC supply. So this field is connected with 220 voltage DC supply through the DPST switch. DPST switch 2, second switch. Then the current flowing through this field winding can be controlled by the rheostat. It is mentioned as R2. So this is a field current. By using this ammeter we can measure the field current. By adjusting the resistor R2 we can control the current flowing through the field winding IF. And this alternator is coupled with the motor. In order to rotate this alternator we are connected with the motor, DC motor. Is supplied with the 220 voltage DC supply. It is connected through DPST1. This excitation we have DPST2, here DPST1. Then 3-point starter is available. Line, phase, line, field and armature. L is connected to the DC supply, A is connected to armature, F is connected to field winding of the DC motor F1, F2. Right, this rheostat is used to control the current flowing through the field winding. So the alternator to find the voltage regulation is available. Field winding is F1, F2 is excited by separate DC supply. In order to rotate this alternator is coupled with the motor, DC motor, that is energized by the 220 voltage DC supply. It is started through the 3-point starter. So this is the circuit arrangement. So we have DPST1, DPST2 and TPST, triple pole. Now we'll see the procedure how to perform the open circuit test followed by the short circuit test. Right. First one, this open circuit test, we'll see the open circuit, then this switch is kept open. During short circuit test, we have to close this TPST. Open circuit test, this switch is kept in open condition. DPST switch, DPST1 is closed, that is energy, that is a supply given to the motor. DPST switch 1 is closed and it is started by the 3-point starter. By slowly moving the starter we can start the motor. This motor is brought to the rated speed by using this adjusting the rheostat. By adjusting the rheostat we can control the current flowing through the field winding so that we can brought the motor into rated speed. DPST switch is closed and motor is started with the 3-point starter. By adjusting this rheostat R1, current flowing through the field winding is varied so that we can brought into rated speed. Now the residual voltage is noted by using the IF equal to 0. Here we can measure the what is the residual voltage. Then we can go to the excitation of the alternator. Now the DPST switch 2 is closed, that is the supply is given to the field winding of the alternator. DPST switch is closed and then the rheostat R2 is varied, and for every variation we have to measure the field current, right? So DPST switch 2 is closed to energize the field winding of alternator, and this rheostat is adjusted. For every variation in the every variation we have to measure the generated IF, measure the IF and generated voltage VOC. What is the generated voltage? That is available here. The generated voltage and IF, these two readings are noted down. So these readings are tabulated. We have to repeat the same procedure until the rated voltage. Until we are getting the rated voltage, we have to repeat the procedure. So I will repeat again. So during open circuit test, first DPST switch 1 is closed. Motor is started with the 3-point starter. Rheostat R1 is varied in order to bring the motor in the rated speed. For that, residual voltage is measured with IF equal to 0. The second thing, DPST switch 2 is closed to energize the field winding of alternator. Then by varying this R2, we can vary the current flow through the field winding IF. For every variation, we have to measure the IF value, field current value, and no load voltage, this VOC, no load voltage VOC. These two readings are noted down, VOC and IF, that can be tabulated. So this is the procedure for open circuit test. Now we'll go to the short circuit test. Before that, what we discussed, the description is available. We can see the description. DPST 1 is closed and motor is started by using the 3-point starter. Motor is brought to rated speed using rheostat 1. Residual voltage is noted when IF equal to 0. DPST 2 is closed. Rheostat R2 is varied, and for every variation, field current IF and generated voltage VOC is noted down. Readings are tabulated. It is repeated until the rated voltage. Right. So for every variation, the field current is noted and VOC line is noted. VOC phase is calculated by using the formula V line divided by √3. Now we'll go to the short circuit test. So during short circuit test, first thing is we have to brought this R2, rheostat R2 in the original condition. Earlier we varied that to bring up to the rated voltage. Now it brought to the initial position. Rheostat connected to the field winding of alternator R2 is brought to the initial condition. Now because of short circuit test, now the TPST switch, this TPST switch is closed. TPST switch is closed, right? This now this R2 is varied in order to apply the rated armature current, right? So the first thing, this R2 is brought to the initial condition. TPST switch is closed. Thereby again this R2 is varied in order to bring the rated armature current. So this armature current can be measured by this ammeter. Using the ammeter, we can measure the armature current. The field current corresponding to the rated armature current, both are noted down. This field current as well as this armature current. For every variation in the field current, the armature current is noted. This is nothing but armature current for short circuit, IASC. So IF and IASC are noted and tabulated in the tabular column. So in this short circuit test, after performing the open circuit test, this rheostat R2 is brought to original position. Then TPST switch is closed. Now the field winding, this field current IF R2 is varied in order to apply the rated armature current that can be measured here. For every variation of IF, this rated armature current is measured. Both IF and IA short circuit are noted and tabulated. Now we'll see the procedure what we discussed. So after the completion of the OC test, the field rheostat R2 of the generator is reduced to the initial position. Now the TPST is closed and rheostat R2 is varied to apply the rated armature current. The field current corresponding to the rated armature current and short circuit is noted down. It's not a set of reading, only one reading. Right? After applying the rated armature current, This field current is noted down, only one reading. In previous case we applied the set of readings. Now it is only one reading. Right? TPST is closed, then rheostat is adjusted to apply the rated armature current, or rated armature current corresponding field current is noted down. Now we'll see the procedure to find the regulation. From these two, open circuit and short circuit test, our aim is to find the voltage regulation. So now see the procedure to determine the voltage regulation. From the OC test, a graph is plotted between VOC and IF, that is called OCC curve. Similarly, from the short circuit test, a graph is drawn between IASC and IF from the short circuit test. So in the both OCC and FC, IF is available. IF versus IA is the short circuit test. IF versus VOC is the open circuit test. Now we'll refer the graph. So this IF is available in the x-axis. Here VOC available in the y-axis. Another parameter IA. So two parameter available in y-axis. So IF versus VOC will give the open circuit test. This is the open circuit test. OCC curve. From IF and IA we can draw the short circuit test. So this will give the short circuit curve. Right. Now from this we need to find the value of ZS. How to find the value of ZS? That is, from the IA full load value, draw the line that will cut the short circuit curve SCC, that is point P. From the rated full load value of IA, armature current, full load armature current, draw the line that will intersect the SCC curve, short circuit curve, that will give the point P. Draw the line, horizontal line, draw the line. So that point, that where it cuts x-axis is the point S. Similarly, draw the line in upward direction that will cut the OCC curve at QC. So this point is called Q. This corresponding current is called a short circuit current, IASC. Right? So I will repeat again. From full load armature current, draw the line where it cuts, that is the point P. Then draw the line downwards where it cuts is point S in x-axis. Draw the upward where it cuts the OCC curve, that is a point Q. From the point Q, draw the corresponding line to the y-axis. So that will give the IASC, short circuit armature current. So from this short circuit armature current and VOC, we are able to find the ZS. From ZS, we can find the E phase, that is the present, that is the regulation. Right. Now we'll see now I think you are able to understand. So in this graph, what we are finding, IASC, short circuit armature current. Now we'll go to the next step. From IASC, we are able to find the ZS. Now find the value of ZS using the formula. What is the formula? Phase EMF on open circuit divided by phase current on short circuit at same excitation. That is nothing but VOC divided by IASC. This only we calculated. The point where Q in the OCC, corresponding current is called IASC, or E1 phase divided by IASC. Now we'll go to the next step. So from the graph we calculated IASC. Now we'll see the entire procedure how to find the E phase followed by regulation. So corresponding to the value of IASC, from the SC test extended to the line towards the SC curve, that is the point P. It meets the short circuit curve at point. What we discussed, the description is available. So from the rated armature current, we draw one line that will cut the short circuit curve, that is the point P. From that we drawn one more upward to the upward that will cut the point P in the OCC. So that will give the short circuit current, IASC. So what we discussed, that is given. So point P, from that we will calculated the point Q. the point where it meets OCC will give the value of E1 phase. It meets the OCC at point Q. Q is nothing but E1 phase. Right? Q will give the E1 phase. Correspondingly, also it will give the IASC. Both are available in the from the graph. Now we'll refer the graph. So the full load armature current, one line is drawn, that is point P. It is downward. We have to draw one more line downwards where it cuts point S, that is E1 phase. Draw the line upwards that cuts the OCC curve called Q. The corresponding current is called IASC. So from point Q we can able to get IASC as well as E1 phase. So from this E1 phase and IASC we are able to find the ZS, right? Synchronous impedance. We know that the normal formula is ZS equal to RA square plus XS square. From that we can find XS equal to square root of ZS square minus RA square. So we need a value of XS. That's why we are called. So this ZS value is known. RA value is already calculated. The first step we are calculated RA. ZS is calculated. Now this ZS is available. So from ZS and RA value we are able to find XS value. Now from that we can find the E phase, then followed by regulation. Now E phase is equal to square root of V cos pi plus IA RA square plus V sin pi plus or minus IA XS, the whole square. This plus indicates lagging, minus indicates leading. Now all the values are known. This XS what we calculated now, right? This V cos pi IA RA all values are available. So for XS only we perform this. This is at we calculated ZS. From ZS we calculated XS. Now from E phase we are able to find the regulation. Percentage regulation equal to E phase minus V phase divided by V phase into 100. Right? So E phase, V phase is already known. E phase is calculated from this formula. In that XS is calculated from this formula. ZS is calculated from the graph. From the graph we calculated ZS. So in this video we discussed how to find the voltage regulation of a alternator. What are the various methods? In that the first method, EMF method, we discussed in this video. That we have to perform the RA. We need to find the first step RA, armature resistance. Then we have to perform OC test and AC test. In that OC test, AC test, the graph is drawn. We are able to find the E1 phase and IA short circuit current IA. These two values are calculated, these are identified from the graph. From E1 phase by IA AC we calculated ZS. From ZS XS is calculated. Then E phase is calculated, followed by regulation. Subscribe the channel for more videos and notification. Soft copy of this material available in the drive. The link is given in the description box. Thank you for listening. All the best for your examination.